let's talk about the beginning of the universe, the beginning of the world. The universe had a beginning, and we know when it was. It was a little less than 14 billion years ago. The more precise number is about 13.8 billion, and the uncertainty on that number is about plus or minus 200 million years now. So we know the age of the universe to within a few percent, which is just a remarkable achievement when you think about it. And the fact that the universe had a beginning at all is a bit of a mysterious thing, right? It leads to other questions. What was before it? What did it come from? What was the cause of this, right? So in many ways, this realization that the universe was not a static and infinite place, this Cartesian universe of Isaac Newton and René Descartes, that was of all of classical physics, where the universe was a static, eternal arena in which physics took place, but that instead the universe is a dynamical thing and actually had a beginning 14 billion years ago, is arguably one of the most consequential discoveries of 20th century science. It completely changed our pictures of where we are and what our position, what our place in the universe is. In modern cosmology, we take this Copernican principle, the idea that we are ordinary, and extend it into what's called a cosmological principle, although I think it really is just simply an honest application of the Copernican idea that the Earth is not in a special position in the cosmos. The cosmological principle is an extension of that, saying there is no place has a special position in the universe. Every place, at least in some average sense, is ordinary, right? So that there's no preferred space. And that immediately tells you, and this was realized by Copernicus and by his contemporary Giordano Bruno and other people who were thinking about this, which means it means that the universe can have no center and no edge, right? Because these would be special positions in some sense, right? So there can be no boundary to the universe, and there can be no center to the universe. And this is central to our picture of the Big Bang. And I think that there's a lot of misconceptions about the Big Bang being, I think a lot of people think of it as some sort of cosmic seed that explodes, like some sort of little dense round thing that explodes and sends stuff going out in all directions. That's completely wrong, and you need to forget about it, right? Because in fact, that center of the explosion would be a special place. It violates the cosmological principle. That's a non-Copernican idea. So a better way to think of the Big Bang is an analogy like this. So imagine I have sort of a stretchable sheet of rubber or latex or something like that, and I draw an even grid of squares on it. So each of these squares is exactly the same size as every other one, and so there's no particularly special point on this. In order for this to fully satisfy the cosmological principle, it has to be without a boundary. So further stretch your imagination a little more and imagine this grid going off infinitely in every direction. So I have an infinitely large grid of absolutely identical squares. This satisfies the cosmological principle. Every spot in this grid is exactly the same as every other spot. There's no center, there's no edge, there's no special position. So now, when the universe expands, right? Imagine these squares getting bigger with time. And as these squares get larger, it still is completely homogeneous. Every spot in this grid is exactly the same as every other spot, but everything has gotten further away from its neighbors. Everything is moving away from everything else, but in such a way that it retains this idea of homogeneity, right? And in the real universe, you can imagine space being filled with identical cubes rather than a two-dimensional analogy here. It's just harder to draw, right? So in 3 dimensions, you might have a grid of cubes where all of these cubes are getting bigger and bigger with time. So this infinite grid of squares, the squares are getting bigger and bigger. Everything is moving apart from everything else. And so if we're sitting, for example, at the intersection of these squares here, and we're looking out at these other galaxies, let me back this up a little bit, right? So if we're sitting here and we're looking out at galaxies that everybody sees themselves at rest with respect to this grid. So as the grid expands, it carries these galaxies with it. And what we see is all of the galaxies, when we look out, we see everything moving away from us. And furthermore, it's not hard to convince yourself that in this kind of expansion that the further away something is, the faster it's moving away from you, because the amount of the distance it moves depends on the amount of space in between you and it. So a space like this actually reproduces the linear Hubble law of saying that the recession velocity of a galaxy is proportional to its distance, or its redshift is proportional to its distance. So this is a better picture of the expansion of the universe. There's no center to this. Every point is identical. Galaxies just sit at rest with respect to this, what's called a co-moving coordinate system, and they all move away from each other as that expands. And everyone sees themselves at rest in the center of this expansion with all the rest of the universe moving away from them. If you were in another galaxy, you'd see the same thing. You'd see yourself at rest, and you would see the Milky Way moving away from you. So what happens when we turn time backwards? Right. So now we can say, let's take a look at this cosmic expansion and run time in reverse and say, what does it tell us about the very early universe? And quantitatively, you can do this with Einstein's equations for gravity, his theory of general relativity. And so as we go backward in time, these squares get smaller and smaller, and everything was closer and closer and closer together. And as we go further back in time, they get smaller and smaller and smaller and so on. And Einstein's equations tell you that at finite time in the past, here, these squares would have gone to zero size. So you plug this into Einstein's equations of gravity, and as you go back in time, all those squares go to a point where they vanish in size at a finite time in the past. This is called an initial singularity. This is the moment of the Big Bang in the standard model of Big Bang cosmology. Notice that even an infinitesimal amount of time after that initial singularity, the universe is spatially infinite in extent. This grid goes on forever. So the Big Bang doesn't happen at one place. It's not an explosion that happens at a spot in space and everything flies away from that. The Big Bang happens everywhere in an infinitely large space at once. An infinitely large, incredibly dense, very high temperature universe springs into being all at the same time, completely homogeneous, and it obeys the cosmological principle, right? So the universe all the way back to the Big Bang is spatially infinite in this model. Right? And the Big Bang happens everywhere in this infinite space at once. It's a boundary in time, not a boundary in space. And the initial singularity cuts off the past history of the universe at a finite time. And that's when the universe goes to an infinite density at the moment of the Big Bang. So this is a very different picture, I think, than most people have of this, right? So how do we work out the history of this cosmos, right? In particular, how do we know that this particular weird model of the universe, with it starting out in this very hot, dense state in which it then cools, right? So as the universe expands, everything in it gets further and further apart, everything gets less dense. And when you let something expand, it cools, simple thermodynamics, right? So the universe would have started out very hot, and as it expanded, it got colder and colder. And in order to do this, in order to work out the history of the universe, we need to use Einstein's theory of gravity, which in the words of John Wheeler can be summarized as matter tells space-time how to curve, and space-time tells matter how to move. And so it's a snake eating its tail. It's a nonlinear process where the curvature of space is created by the matter that lives within it, and the motion of the matter is governed by the curvature of the space that it has created. So in order to understand the history of the universe, we have to describe the stuff that's in it. And cosmologists divide stuff into three kinds. The first is just called matter. And what a cosmologist means by matter is anything that is sort of just like atoms or dust or gas or maybe dark matter particles or something like that. Anything that can be described by, more technically, a non-relativistic particle, right? Something that's basically at rest. And so imagine if I have a cube now, so I'm doing this in 3 dimensions. So imagine I have a cube full of like hydrogen atoms or something. If as the universe expands, that co-moving cube gets bigger, but the number of atoms inside of it doesn't change. So the density of the atoms drops as the inverse of the volume of the box, right? They become less and less dense. These atoms become more dilute because the space is expanding, but the number of atoms is fixed, right? So the amount of energy per unit volume in this box drops with expansion. The second kind of stuff that cosmologists use, we just call radiation. And this might be photons or leftover from the Big Bang. We'll talk about those, or neutrinos, or any essentially relativistic particle, anything that's massless traveling at around the speed of light. And this this radiation also dilutes with expansion, but it dilutes a little more quickly than the matter, because in addition to the number of particles, the number density of particles, the number per unit volume dropping with the expansion in exactly the same way the matter does, the radiation also has redshifts. It loses energy because the wavelength of the photons stretch as the expansion continues, right? So when a photon propagates through this expanding background, it actually gets stretched out by the cosmic expansion and gets longer and longer wavelength as time goes along. And so they lose a little bit more energy because of that redshifting. And so the total energy in the box dilutes more quickly for radiation than it does for matter. All right, so this stuff, the relativistic things, dilute more quickly than the non-relativistic things like atoms or something. So photons dilute more quickly than atoms, right? The third kind of stuff is called vacuum, which is essentially the energy of empty space. And this will become very important later when we talk about inflation. And basically, if you assume that space itself has some sort of non-zero energy associated with it, and we believe this to be the case in the current universe, this is the stuff that's called dark energy, then if the space itself has an energy to it, then the energy density stays constant, right? So as this box gets bigger, the total amount of energy that's contained in the box actually increases. So if you have a constant, amount of energy per cubic meter and the number of cubic meters in the box grows, if there's more vacuum in the box and the vacuum has energy, then the amount of energy in the box is going to go up. This might seem like it violates conservation of energy, and which is true, it does. Sorry. I mean, energy is not conserved in general relativity globally. There's still a local sense in which it's conserved, but general relativity allows you to break energy conservation in this way. In particular, because it's time dependent. You no longer, and energy conservation is associated with symmetry under time translations. If you have a time invariant system, you have no reason to expect that energy is conserved. And in fact, in cosmology, it is not. It's also the same here with these photons. These photons, a light wave traveling through empty space loses energy due to cosmological expansion. That energy doesn't go anywhere, it just loses it, right? So this is another example of violation of conservation of energy in cosmology. But it's most prominent in this vacuum energy, where you actually just get more and more energy out of nothing as this box expands, if empty space itself has energy. And this is a key to this theory of inflation that I'll talk about later on. So this means that because, and now the vacuum doesn't dilute at all, right? So matter dilutes slowly, radiation dilutes more quickly, vacuum doesn't dilute at all. So if we turn time backwards, that means that there are three main epochs in the history of the universe. Before about when the universe was about 60,000 years old and earlier, and a temperature of about 10 to the 4 Kelvin or higher, the universe would have been mostly radiation, relativistic species like photons and neutrinos and light particles, right? These diluted away more quickly, and then at about 60,000 years after the Big Bang, the universe transitioned into being matter dominated. So things like hydrogen and helium and dark matter and so on would have been the dominant energy density in the universe. Up until the universe got to a temperature of about 5 Kelvin, a little less, about 3.5, which happened about a few billion years ago. Actually, while there was still primitive, while there was primitive life on Earth, the universe went through another transition in which the matter diluted away, and this residual vacuum energy started to be the dominant component of the energy of the universe, and it is still today. So the vacuum energy now, in fact, makes up about 75% of the energy density of the universe, and the matter and radiation are the other 25%. And because the universe was, everything was squished together, the early universe would have been very hot. And so as we go backward in time and up to higher and higher temperatures, our understanding of this gets more and more speculative, right? So at a very high temperature, we would need a theory of quantum gravity to undo it. We don't have such a theory. That would be about 10 to the 32 Kelvin temperature. Going downwards, so dark matter forms somewhere in here. We don't know really where. The Higgs field gave mass to the standard model particles at a temperature of about 10 to the 16 Kelvin. Quarks form bound state at a temperature of about 10 to the 12 Kelvin. The first nuclei formed when the universe was about 1 second old at a temperature of about 10 to the 10 Kelvin or so. Electrons and their antimatter counterpart annihilated a little bit after that, so on and so forth, all the way down to today. The first stars formed maybe when the universe was a couple 100 million years old at a temperature of about 20 Kelvin. The current temperature of the universe is about 3 Kelvin, right? So we can work out this thermal history of the universe, and we understand it pretty well, and we have observational constraints back to about 1 second when the first nuclei formed. We can figure out, we can constrain this by looking at the abundance of primordial abundance of elements in the universe today. Anything before that is much more speculative and theoretical.